Good evening. My name is Kaluge Salim and I'm here representing Group 9. Our project is about generative attention-based mechanisms for fake currency node detection. My group member, Kashar Alvin, will come in to talk about the preceding slides. And I'll begin by talking about the background of our study. Of course, we know counterfeit currency is a major threat in all the economies in the country. And over the world. For example, we all know that in Uganda, if I'm to bring this down to Uganda, we know that in Uganda, in December last year, Postbank was given fake notes. It gave out fake notes of around 500 mil to a client. Of course, it gets surprised, it being a bank. You wonder why should it be happening in a bank, and yet we know that these banks are the ones which are trusted by clients. But this is where we come in as the Cash Intel AI and as the generative adversarial learning and graph attention mechanisms team to cap down this. We know the financial risk of the fake currency as disrupts economies and the security challenges it brings the economies because these funds, the counterfeit currency funds illicit activities. For example, rebels can use them to buy fire weapons. And then the traditional detection, manual and UV light infrared scanning are all slow and ineffective. Then we are having a lot of methods that we had used in our project. We are having the feature extraction, whereby we used the k-nearest neighbors, the support vector machines, and the neural networks. We're having the image processing combined with automation systems for counterfeit detection, is the UV light analysis, polarization analysis, edge detection, and image segmentation. Then another method, we're having statistical feature extraction for banknotes and supervised classification. We use decision trees, random forest, support vector machines, and others, as you can see. Then the problem statement, of course, beginning with a domain-specific domain application problem. We know that traditional methods of fake currency detection, such as money infection and UV light, these ones are prone to counterfeitism. And as a requirement, we need to come up with a deep learning technique, a deep learning project that can help us cap down these sophisticated counterfeitism techniques that have been brought about by people with very well organized and clear instruments that can print out these real notes. So on the computational problem, we are having a lot of computational problems. I will bring them down to 4. We are having attention mechanism for important feature localization. In this sense, we shall be using image feature extraction, for example, VITs and the graph attention networks for feature extraction. And of course, here we shall be having ORB and the Delaunay translation for feature extraction and graph drawing, respectively. Then also have adversarial robustness and defense. Here we are having generative adversarial learning for coming up with samples which can be able to withstand robust and hard conditions, counterfeits. Then you have data augmentation. Because of the limited data set we had, you had to use data augmentation to come up with more and more samples to use in our training data sets. Then on the research questions and objectives, as you can see, we are having a research question saying, how can generative adversarial networks be utilized to enhance training data set of fake detection? Of course, here the objective becomes to enhance model performance by generating synthetic counterfeit currency using GANs. We shall be using GANs, like I had explained in the previous slide. Then improve detection using vision transformers, GATS, and noise distillation. I also have to explore the potential of ensemble learning. Ensemble just means combining different models, come up with a clear and effective model which is fine-tuned. Then on the research continuation, and outputs, we developed a graph attention network to improve fake currency detection by capturing key features and relationships. Of course, here we use ORB for feature extraction, and then the Delaunay translation for drawing these graphs. Then we implemented vanilla graphs We also develop vision transformers. Of course, these ones use patch detection, and it divides each image into patches. Then also apply the ensemble. We combine different models to come up uh, with classification, real versus not versus fake notes. Then we also develop knowledge legislation, student model versus a teacher model. And then on the methodology, we are having, of course, a methodology. You have the problem definition, which clarifies. We are trying to differentiate between fake from real. And then from there, I have to do data preparation. Data preparation, this is where I get our data set and prepare it. Um, to make sure it's balanced and nothing like overfitting and underfitting. Then we have the model design. Here we get different models and then try to train them. After training them, evaluate them to come up with a best model. And of course, after getting a best model, we deploy it on render or print card, depending on what we want. Other system architecture. System architecture, we are having user interface. Then the user interface, we upload the image using the Flask API. And then this Flask API, inside the API, we do the data pre-processing, feature extraction, and graph construction pipeline that I explained. Of course, we are using the GAT, then the prediction is brought back to the user interface.
Good evening, everyone. My name is Kasha Alvin Sali, and I will be continuing from here. For the dataset description and explain analysis data for the data. The dataset was first of all obtained from a public Git repository, and it contained denominations of 5,000 and 2,000 Indian rupee images. As you could clearly see, this is for the 500 Indian rupee, then the 2,000 Indian rupee, with various security features such as the security thread, the domination line tint, and also the other different watermarks. So this is a simple bar graph showing the different distributions of images as per the different folders, and then also the distribution of brightness among all the images. The frequency simply means the number of images, and then the brightness level, as you could clearly see. So next, these are some of the results that we got after training the models on our data set. As you could clearly see after till the end, this was for the vision transformer that classified real images as real on the 6, then misclassified 1 real as fake, then misclassified 1 fake as real, and then 5 fake as fake. Then this was its learning rate, as you can clearly see, starting these are number of epochs, the number of times the model was trained on the dataset, and then also the learning rate. The maximum was 0.01 as we are tested for the vision transformer. So it could see it first learned constant, then over the various number of epochs as well training on the data, it eventually maintained a constant state, showing that it had learned all the features in the dataset on the images. Then this was the training and the validation actually see for the RaceNet. As you could clearly see that the training actually see that represented in blue was clearly increasing under the number of epochs, and then clearly, yeah, like that. But then after that, the validation was under this, and it was clearly showing that it was not validating on the training data. Then the very same, the loss function, you can clearly see that this time round, it's the validation loss that is actually dropping steeply, and then the training loss is also dropping timidly at the end of the number of epochs. Then this was just the model metrics for the ensemble learning random forest, and you could clearly see it achieved this accuracy. It was actually in 70 something, and then the precision, then the recall F score, and then this was the confusion matrix for it. Then this is the table that shows the performance metrics of the all models. We implemented 10, and by accuracy, precision, recall, and F1 score, the GAT was chosen to be the best performing as per the accuracy. It achieves a 90.62, then balanced precision and recall nearly with 88 to 9.2%, and so the F1 score was 9.4. Then our poorly performing models was the RaceNet with 59.4%, and the MobileNet with 60.3%. So as my colleague had earlier told you that we ought to have developed a GAN, of which we did, but it kind of developed images, fake samples, those synthetic data images that were supposed to be used to enrich our data set and improve model generalization. The images that developed were of low quality just because we had little or limited computing resources as per our computers. So we did not achieve the targeted image quality as we wanted. So instead of this, we opted for data augmentation as we came up with different copies of the data set, and we made our data set rich enough to improve model generalization. But these were the samples of the images that you could clearly see. This is one that was produced on our vanilla gun. It's for 500 knot, and then this is a 2000 knot, but you clearly see they are not very clear. Then this is a training loss over the epochs for the mobile net. As you could clearly see, the loss was actually decreasing, but then it had a shift stitch over the epochs that were trained, and then decreased sharply, and then continuous up to the last epochs of 50. Then this was the training loss by against the validation note as well. Then you could clearly see the validation accuracy was above the training accuracy, meaning that the model was actually learning from the data set. Then, of course, we ought to apply explainable AI. Yes, explainable AI to our models and know why actually where they focused. So our best performing tool were the GAT and Vision Transformer, and you could clearly see using the BradCam explainable AI technique. It clearly showed us the features that the GAT focused on to carry out its prediction, and these were in ink of red. You could see clearly that these are the security features of the node having the relative domination, then the signature of the governor, the security thread, and others. Then we also implemented silence maps to show the key points and the key point importance that the GAT give attention to, and clearly you could see still they are the security features. Then for the Vision Transformer, I'll use lame explanation to note out those features that the inbuilt feature extractor of the Vision Transformer gave attention to, and you could clearly see most of them that are circled with this orange are the 500 domination, the security thread as itself, and then the signature of the governor, then also others. Then also applied sharp values to have the feeling of the pixels that the Vision Transformer ought to have applied its attention mechanisms, and you could clearly see that those that were depicted in orange and clearly near to green, those were the ones that it gave most attention. You could clearly see these ratings, and here the bankers, the governor's signature, Magadi's face facing to the right, and then also other security marks. Then for the least performing, we had the mobile net and the RESTnet. So for the RESTnet, you could clearly see it did not, the blue regions on this image show that they're the most important features, but RESTnet missed out on them. Then the rest, rather that was a mobile net, the RESTnet also shows that it missed out on this. Then also applied the M explanation, and you could see M explanation. These were the features that the RESTnet learned for classification, and you clearly see it only identified a few of them and neglected the most important values. Then this was the contour map as per. This was attention rollout. This is GradCam. You could clearly see Magadi's face behind and a few features. So these models, the CNN models, were not able to pick out the most key important features on the data set and the images. Then why we chose the GAT, it's simply because it obtained the top performance, then the stability, that as the idea said, the balance, precision, and recall. Then also first study point, since it was a light model compared to the heavy CCNs and the VITs. Then also the visual attention as well. Then this was our system architecture. My colleague had taken you through, which I want to go back. Then this was our user interface, where you could clearly insert an image. Then here you get a prediction in real time. Then the IP assets, but the quantitative aspects were the model itself, the unique processing pipeline, the real-time Flask API for the currency node detection. Then the copyrighted aspects were the Flask API cap, then the GAT model implementation, the training scripts, and the documentation. Conclusions, I ought to say that we developed a number of machine models, as earlier showed, with more than 10, but the key accomplishments we had, it was improved accuracy as the model. The one we deployed, the GAT could classify fake and real notes, and also generated synthetic data, fake samples, though they were of poor quality, but still they were an achievement. Then also Vision Transformers, and also we developed a knowledge distortion model that has the GAT as the teacher, transferring knowledge to the student teacher as the CCN. Then the limitations, we had a limited data set, as my colleague had earlier said, limited resources. That's why the GAN produced low quality images that are imbalanced. Also addressed that using data augmentation, then the data quality in terms of the images that were. Then the next steps are for the future works, using we ought to transition from traditional paper-based currency towards fully digital money systems. This is the future for the cryptocurrencies. And also, as digital money grows, fraudsters also may still want to target the traditional cash system. So our system would be automated and deal with that. Acknowledgements go to the Makerere Intellectual Property for helping us come up with the AP assets of our project, and also Makerere University Innovation Pod for the commercialization and expansion and scalability guidance to our product. Thank you very much.